All right, hello. Welcome to EEE 117. This is chapter 10, part 1 of the network analysis. So I'm going to go ahead and jump right in. Last week we covered chapter 9, which is basically a review of phasors. Here we're going to go ahead and move on to actual single-phase power. So if you're going to be a power engineer, going to power industry, this is probably the absolute most important part of your engineering career to pay attention to, because we're going to cover basic of single-phase power in the AC systems. So first thing we do, let's talk about power. How do we calculate instantaneous power? Well, remember, P is always V times I. Now, because current and voltage are sinusoidal, there's cosine, VM cosine omega t plus theta. You have to put the little bracket t because they're time varying. So this isn't like DC where it's just like 100 amps time or 10 amps times 120 volts. It's a little more complicated than that with cosines. So there's gonna be some complicated math involved, some trig shenanigans. So if we directly multiply these two, as we should, as per mathematics, you can have Vm cosine Wt plus theta for V times Im cosine Wt plus theta for I. This doesn't help us yet. We got to combine these cosines together with some trig functions. Now, this isn't a math class. I'm not going to go into details. Textbook has it if you really want to dive into it. But at the end of the day, instantaneous power is going to be equal to Vm Im divided by 2 cosine of theta V minus theta I plus a bunch of other stuff. Everything else is very important to note. There's a cosine 2Wt here and a sine 2Wt here. So what this means is these two terms in blue, they're still cosine and sine functions. They're still oscillating up and down. The first one, even though there's a cosine there, does not have a t involved. So if we ever do calculations, this term is actually a constant number. So which term is constant? It's a Vm Im divided by 2 cosine of theta V minus theta I. Very, very important to see this. So this means this red part, it stays the same throughout the whole circuit. The blue part goes back and forth and oscillates all over the place. Okay. Which terms are sinusoidal? Anything with the time variable t. So the second cluster here and this third cluster here. Okay, so one constant part, two oscillating parts. So how does this help us, right? I mean, like, there's a giant math ball. What does that tell us? Well, this is where we could go and look at the waveforms and say, hey, here I have a voltage in the dotted line. That's my original voltage. This is my original current in the solid black line. Notice they're not on top of each other, so there's a phase shift, okay? If you multiply V times I at all points along these lines, you're going to get this blue curve, the power, instantaneous power P, okay? See how it goes up and down? So yes, it's oscillating back and forth. But notice that the center of the, we'll say, the cosine, or not, it's a combination cosine sine. The trig function, right? The sinusoidal, let's call it that. The center is not on the zero axis. We're so used to the cosine and sine functions floating up and down across the zero axis. This one is a little bit above. So in red, I drew where the center would be. So it's equally oscillating up and down across this red bar right here. What does this mean? This is our offset. So offset means is we have a sine and cosine function. We're just adding a flat +5 or +10 to that number. So we're raising the whole function up, which kind of makes sense because remember, there is a permanent constant in red, and then there's a bunch of sinusoidal functions. So it will make sense that the whole function as a whole moves up by that red offset, and then you still have the oscillating blue part. Okay, so it's very important to understand instantaneous power will have a flat, constant DC offset with the oscillating part as well, okay? Now to kind of show this is our function again. Let's concentrate on that constant part. So instantaneous power goes up and down all over the place. But what's more important is how much energy is being permanently dissipated in the load. So if you turn a light bulb on, there's going to be a permanent amount of energy that goes from the source to the light bulb. We need to figure out what that permanent energy flow is. It's not going to be oscillating back and forth. It's going to go to the light bulb and then burn up. But remember, this function is so complicated, we can't just say, well, what's a hard number out of it just yet. But there's a math function we can do to take the average of this entire waveform, the blue one, to get what permanently goes to the light bulb, right? And that's where we take the averaging effect. So we have something called average power, capital P. So capital means average. Is equal to 1 divided by t of an integral 0 to t. So all this 1 over t integral, remember, integral is adding up over the whole function. So between two posts, we're just hard adding the numbers, and then we're going to average it by dividing it by t. So this is just a standard averaging function you've learned in like elementary school. Take 10 numbers, add them all up and divide by 10, that's your average. That's what all integral does. So we're going to average this instantaneous power. Now, the beauty of this is because you have these cosine and sine functions, what happens when you take an average of a cosine or sine function? It immediately goes to 0 because you got the positive half, negative half, they cancel out. So the second term and third term immediately go to 0, and all that's left is that constant we keep talking about. Remember, this is a DC offset. So this type of average power is Vm Im divided by 2 cosine of theta V minus theta I, right? This is called the real power, the average power, or the active power. There's 3 different ways to call it. The book calls this average power. That's like a mathematical term. I've heard real power and active power as well. What matters the most is this is the amount of power that gets transferred to the load and used up. So if you have a heater running, it's going to be you're using this real power, this average power, right? Because the electricity, the energy goes from your wall socket to the heater. It's not going to ping pong back and forth. Once it goes to the heater and turns into heat, it's gone forever. Okay. The units that our average power represents is watts, but watts is a small units, especially in the household. So sometimes we use a kilowatt, which is 1,000 watts. If you're in the power industry and you're generating for a whole neighborhood, you're going to be using some megawatts for like a kilowatt is typically for a household. So one house maybe has 1, 2, or 3 kilowatts, depending how big it is. Individual watt is for like a single device. Like your cell phone might take 5 watts to charge. Megawatt is for an entire subdivision. So 100 homes or so, or 500 homes might take a megawatt to power. Okay, so it just depends what type of equipment and how big a scale you're talking. We'll use watts, kilowatts, or megawatts. Excuse me. So remember, average power is average. We could go up here. Actually, I think it's on this next slide over. Yes. So here, remember we talk about this averaging effect. So we had that constant part, and then we had those oscillating energies. So think about it, this is visually what we're doing, averaging. So notice blue is an instantaneous power. Now, every time we take the voltage and current, we're multiplying it through. So between these 2 points right here, you have a positive current, but a negative voltage. So when you multiply a positive and negative, you can get a negative number. That's why this instantaneous power in blue dips below the 0 line. So you can think about from this point here to the second point, this distance in purple, this is where we're having negative power flow. So this red part is actually taking energy from the loads for a very short time. So when we're averaging the positive half, which is our P, or average power, we have to take some of that red half that was negative and chunk it out of the positive half, right? Because remember, we're adding together. If this negative half is negative 100, you have to take a positive 100 and chunk them out, and they'll cancel out. And then whatever is green is going to be the actual average at the end of the day. Okay, so that's visually how I like to think about it, is the more lopsided the blue waveform is to the top, the more net positive average we're going to get. If this blue waveform falls lower and lower onto this zero axis, we're going to get a little less of an averaging effect. We're going to get more of this red cancellation effect. Okay. Now, the big thing is, the bigger this distance between the two negative points, the more of this red cancellation effect we're going to get. Okay, so you see, we like to call this cancellation effect the oscillating power. Because what's happening electron-wise is, for this negative half, the energy is actually going from the load back to the source. And then a positive half, some of that source energy that we gave will come back to us. So for a little bit of the energy is going to literally go back and forth all day long between the load and the source. Okay. The blue positive, the green permanent energy, that's more of the heater and the loading, the real work being done in the circuit. Okay. Now, as this difference, these two blue dots get further and further apart, you can get more oscillating energy on the bottom that you got to take from the top. So this is a very, very important concept. The bigger phase shift is between a voltage and current. So you have a voltage angle and a phase angle. The farther and farther apart they get, the more this oscillating energy we're going to get. Okay. And it gets bigger and bigger. And that's relatively a bad thing, right? It's inefficient to have this oscillating energy in the circuit. Okay. So it's a good way to visually show how does this averaging effect work. Okay. So we know capital P green, that's good. We want to keep this. But how, and we could quantify this with average. But how can we quantify the red part, right? Because, I know as it gets bigger, we need more, but I need a hard number. You see, P, I could get a hard number just doing the math, but I have no way to represent red from this equation. So we have a new term called reactive power, right? So we have the green, which was the real power or the average power. This represents an oscillating part, and we call it reactive power. Now, out of this equation, what represents a reactive power the best is this last term, mainly because you have to subtract it from the instantaneous power. Because remember, we talked about this is cutting away from the averaging part. See up here, remember, we're subtracting from the averaging part. So that's why we use this negative value. Additionally, because it's a sine function, the bigger and bigger the phase shift gets, the more and more this negative number grows. Okay, so we could take this number right here and define a new power called reactive power, and they like to use capital Q. And capital Q is going to be equal to Vm multiply Im divided by 2 sine of theta V minus theta I. Okay, so this is just a math thing you're going to have to memorize. And this represents that oscillating energy, that red pocket. Another way to call this reactive power, actually I said reactive power twice, is imaginary power, right? So it is called two names, reactive power and imaginary power, okay? I think reactive power is probably the more formal way to say it. But a lot of people like to say imaginary power as well. And the reason why I say imaginary, because it's not doing any actual real work. It's kind of wasted. So it's kind of imaginary in the sense that I'm getting nothing out of it. Okay. Now, what type of units we're going to use for this? We're going to use volt amperes reactive. They say volt amperes because it is voltage multiplied by current. And they put reactive to represent that it's reactive power. Otherwise, you might get confused because volts times amps is instantaneous power. So we need to make a difference. The reason why we don't use any formal like watts is because there is no SI equivalent number for this, because this concept of reactive power is only in power engineering. There's nowhere else in science that we talk about this. Okay, so volt amperes reactive, we shorthand, we call VARs. Okay, you can say we have VARs, kilovars, megavars. Okay. Now, remember, So let's put it together. Main components. We had instantaneous power. We broke it up into two major components. Real power up here, which is the average power, that's permanent energy flow. So P equals Vm Im divided by 2 cosine of theta V minus theta I. We have reactive power Q, which is Vm Im divided by 2 sine of theta V minus theta I. Conveniently, the only difference between these two is a sine and a cosine. That's why it's a little bit easier to remember. So all just remember is Vm Im divided by 2 and a trig function. Cosine for power, sine for reactive power. So cosine for average real power, sine for reactive power. Okay. Now, question is when do we have the maximum amount of real power? Well, remember what a cosine function does. To maximize a cosine function maximum is always a 1. And when is this 1? Is whenever the phase angle is 0. Right? That's just part of trig you probably memorized by now. So it's good to note that if I want to maximize my real power in the circuit, I got to make sure my phase angle between the voltage and current is 0. There's no difference. They're purely in line. Because then what happens is that large instantaneous power waveform is going to be all positive. It's going to be no negative half. So there won't be any red value to chunk out. Okay. Conversely, how can we make reactive power 100? How can we have all reactive power? Or how do we maximize reactive power? Well, this is a sine function when this is sine 1 or negative 1. Right? We can maximize the sine function by having the phase angle difference between the voltage and current to be either positive 90 degrees or negative 90 degrees. So the more and more the phase angle shift between voltage and current to plus or minus 90 degrees, because that's about the maximum you can realistically get, you'll have the most amount of reactive power. So at this point, if you're at one of these 2 points, that instantaneous power, that really big waveform, it's going to sit right on the 0 axis, right? It's not going to have a positive DC component, because for this Q to be at positive 90 degrees, this cosine is going to be at 0, because cosine of 90 degrees is 0. So at these 2 maximums, one of them is 100%, the other one's 0%. Okay. But just they're paired up like this. Right? So the best way to look at this is you guys see the math involved, right? So with single phase power for a resistive circuit, so we just have a pure resistor. Well, I want to calculate the real power and the reactive power, P and Q. Again, as a power engineer, you're going to talk about P's and Q's for the rest of your life. So the first thing we need to do is we need to find the current. We know voltage is 120 volts at an angle of 0 degrees, frequency is 60 hertz, R is 10 ohms. So Ohm's law is current I equals V over R. So 120 angle 0 degrees divided by 10 ohms, so it's 12 angle 0 degrees amps. So notice that the angle of the voltage is 0 degrees and angle of current 0 degrees. So immediately you can see there's no phase shift. So it should already give you a hint of what's going to happen. Calculate the real power P. P is Vm Im over 2 times cosine at an angle difference between the voltage and current. So we have 120 for volts times 10 for current divided by 2 cosine of 0 minus 0. That's 1. So 120 times 10 over 2 is 600 times 1. We get 600 watts. So this resistor is outputting 600 watts of real power. What about reactive power Q? Oops, sorry. So here, almost, I had the green arrow was awesome. See if I can get it back. Nope. We'll just keep going. So you have Q right here. This is Vm Im divided by 2 sine of the angle difference between the voltage and current. Theta V minus theta I. Let's do the math here. This part doesn't matter because sine of 0 minus 0 is 0 anyway, right? So this whole term cancels out, so we get 0 VARs. So the big takeaway here is for a purely resistor, It'll always have 100% of its power to be real and 0% of it is reactive. Okay, so it'll always be real power. So if you ever do a calculation, you get reactive power coming off a resistor, you definitely did something wrong. The other big thing to take away here is a resistor will always take energy out the circuit. It never oscillates energy. There's no energy ping-ponging back and forth between the source and the load. Every ounce of energy, every electron that goes to the resistor will dissipate its energy off the resistor as heat or a function of light. Okay. So that's the resistor. Always do the simplest case first. Next, let's do it in an inductor. This is where it's going to get kind of a little strange. Because remember, what does an inductor do? Does an inductor have any permanent energy dissipation? No, it doesn't do any permanent work. An inductor doesn't heat a house. It doesn't light a light bulb, right? Inductors are energy storage tanks. So what happens in an AC system? For one half of the cycle, you have to build up the magnetic field. The other half of the cycle, when you go negative voltage, you're going to have to take the energy out of an inductor. So by nature, what an inductor does, it takes energy from the source for one half of the cycle, and the other half of the cycle, it spits the energy back to the source. So this inductor is literally just ping-ponging energy back and forth. So from a physics standpoint, you could probably guess what's happening with a P and a Q. But let's do the math to make sure we're right. So again, Ohm's law, you got I equals V over that's a Z, that's an error. So that should be a Z technically, but we'll keep going, right? So this is J X of L. X of L is 10 ohms. So you'll have 120 angle 0 degrees. Now remember, it's a J. This is an inductor. So you're going to have a positive 9 degrees. Anytime you have a J, that's always a positive 9 degrees. So you have 120 angle 0 degrees divided by 10 angle positive 9 degrees. Do the math, you're going to have 12 angle negative 9 degrees. So immediately you can see between the voltage and current, there's a 90-degree phase shift. Again, that's giving us another hint of what's going on. So calculate the real power of P. P equals Vm divided by 2 cosine of the angle between the voltage and the current. Don't have to worry about the first half because we know the second half is 0. Because you have a 0 degrees minus a negative 9 degrees. And that's a positive 9 degrees. Cosine positive 9 degrees is 0. So you're getting 0 watts. So it tells me that this inductor is not taking any real power out of the circuit. It's 0. What about reactive power? All right, this is where we're going to pay attention. Vm divided by 2 sine of theta V minus theta I. So let's punch some numbers in. We got 120 volts. We got 10 amps divided by 2. Sine of 0 degrees minus negative 9 degrees. So we're actually going to get a positive 9 degrees. Now, you do have to keep track of the negative or positive here because the signs have different values depending on positive and negative inside the phase angle. Cosine does not. So sine of a negative 9 degrees is a sine of a positive 9 degrees, which is a positive 1. So here we're going to get 600 VARs. So what this tells me is this inductor is releasing or taking up 600 VARs of power. And this is the energy that's going to the inductor and releasing it back and going back and forth. Okay. Now, somebody will ask, well, if we're not doing any real power, does it take any effort? It still takes effort to build the magnetic field and break it down, build it and break it down. So energy from the source is being used to always fight that magnetic field, but we're not getting any permanent work done. We're kind of just spinning our tires in the mud here over and over and over again. Okay. So inductors, remember, they absorb 0% real power, and they're always 100% reactive power. So they're always absorbing reactive power from the circuit. Okay. Let's talk about a capacitor. So capacitor here is negative 10 ohms. And let's think about what's going on here. So we have a bucket of energy, right? We got that giant cookie sheet, lots of electrons. So what's happening here is on the positive cycle of the voltage, we got to take current to fill up the bucket of energy. On a negative cycle, that bucket of energy can get dumped and go back into the source. So it's the same thing here as an inductor, is that there's an energy swap in between these two, right? So energy is going to the source and back to the load and back to the source. So there's a lot of reactive power being used here. Okay, so we could do the math to see how much. So same thing, Ohm's law, where the difference is that we have X of C is -10 because it's a capacitor, right? So the big difference is we're gonna have a -9 degrees for an impedance rather than a positive like the inductor. So your voltage is 120 angle 0 degrees divided by impedance of 10 angle -9 degrees. Do the math, we're gonna have 12 angle positive 9 degrees amps. Because remember that the current always leads the voltage in a capacitor. Calculate real power. We're going to go through all this because we know we have a 9 degrees in cosine. It's going to be equal to 0. So capacitor does not have any real power dissipation. It's all reactive. Calculate the reactive power. VMIM divided by 2 sine of theta V minus theta I, the angle between voltage and current. You have 120 times 10 over 2, that's 600. Sine of 0 degrees minus a positive 9 degrees. So remember, sine of -9 degrees is a -1. So this is something a little unique. We haven't seen this before. We're getting -600 VARs. So what does -600 VARs mean? It means that capacitor is supplying 100% reactive power and 0% real power, right? So a capacitor, in terms of power, actually supplies VARs into the system. It's acting like a mini generator for reactive power only, okay? And the reasoning here is that instead of taking energy and having to build a magnetic field, the energy is already in the capacitor stored as a bucket. So anytime we try to change it, the bucket is ahead of us and dumping energy out for us. So again, the capacitor in terms of voltage is always thinking ahead of us. So anytime we want to change the voltage, the capacitor immediately dumps all its energy out to get ahead of us. That's why it's supplying the energy into the system. Okay? It's already there. The capacitor already has the energy to supply it in. An inductor, to that magnetic field, always will need energy to build it, so there's always going to be a delay in getting it going, right? So inductors will always need VARs to operate. A capacitor will always supply VARs to operate. So capacitor and inductors kind of pair up very well together. If you have a capacitor nearby an inductor, they can actually supply each other energy to help build and break down the magnetic field and the charge the bucket of capacitor quicker. Okay. So that's your capacitive, inductive, and resistive circuits. So far we're focusing mainly on the math, right? I mean, it's circuit analysis at the end of the day. So here we're going to take our small break, 15, 20 or so minutes. Pause the video, right? We're going to have an exercise for you. We have a single phase power. I want you to calculate the real power. And next page, I want you to calculate the reactive power. It's going to be a little different from what I did before because you have a resistor, and an inductor. So your impedance is going to be a little more complicated. So you figure out your Z impedance and you go through the same steps of figuring out the current and then figure out your P here and your Q here. Okay. So because you have a resistor and an inductor, you're going to have some level of real power being dissipated by the resistor, some level of reactive power being dissipated by the inductor. So you're going to have a little bit of both. Okay. So like I said, we'll pause it and we'll come back in 15, 20 minutes and see what you guys did. But good luck. See you in a little bit. Okay, welcome back from our 15, 20-minute break. Let's go ahead and check out this exercise on this chapter 10, single phase power, part 1 section. All right, so first off, we have current. So current is always VI over Z, or voltage is 120 angles 0 degrees divided by impedance. R and JX are in series, so we add them together. So you have 10 plus J10. So 10 plus J10. Don't forget J for an inductor. It's very, very important. Number crunch that's 8.49 angle -45 degrees amps. So let's figure out power, real power P, Vm over Im divided by 2, cosine the angle difference between voltage and the current. Number crunch 120 times 8.49 divided by 2, cosine of 0 degrees minus a -45 degrees. So double negatives. you will get a total of 360.2 watts. Okay. Let's go do the same thing for reactive power. So the current is still the same because it's in the series circuit. So it's the same current going through to both. That doesn't change. Reactive power, Q is Vm In divided by 2 sine of theta V minus theta I. So again, if you're ever using a calculator, it's actually really easy to calculate reactive power because you just hit second enter to get the same equation and just swap cosine with sine and hit enter again. So you're going to have the angle difference is 0 degrees minus negative 45 degrees. So you have total positive 45 degrees in the sine function. And you will also get 360.2 VAR. So actually, the Q and the P are actually equal in this specific circuit. And that's because the inductor and resistive impedance are equal. Because they're equal, they're going to have the same amount of reactive power and real power put out. Okay. Additionally, sine of 45 degrees and cosine of 45 degrees have the same number as well from the trig standpoint. Okay. But a big thing I want to show with this circuit is you can have one circuit with multiple resistor and inductor and have both P and Q in the same circuit. So this source had to put a real power P and a Q reactive power out at the same time to satisfy both of our loads. Okay. Or the resistor and the inductor. Okay. So it was just very basic to show, hey, this is how real and reactive power operate in a very basic circuit, right? And of course, we're going to start building off of that. So big thing here, I want to compare real versus reactive power for the different type of circuit you're going to find. If you have a purely resistive circuit, so it's just a resistor in it, the voltage between the current and the voltage between the voltage and the current will always be 0 degrees because the resistor has no J impedance. So and anytime when you do Ohm's law, there's no J involved, so you're not going to get phase shift difference. Okay. Now the voltage might have a phase shift, but the current will have the exact same phase shift, and then they'll cancel out. So just remember, this is always the difference between the voltage and the current. So because there's no phase shift difference, you're going to absorb real power, and you're going to have no reactive power at all. Okay, that's what 0 degrees mean. If you have a purely inductive circuit, you're going to have exactly positive 90 degrees. So it's only an inductor in the circuit. You have a positive 90 degrees phase shift between the voltage and the current. You'll have no reactive power, and it'll be you have no real power P, and your reactive power Q will be absorbed from the circuit. So an inductor always absorbs reactive power. If you have a capacitor in the circuit, your phase shift, the phase angle difference between the voltage and the current will be negative 90 degrees. Again, no real reactive power is being absorbed, and you are supplying, no real power P is being absorbed, and then you're supplying reactive power Q into the circuit. Okay. If you have a resistive and inductive circuits, this is probably the most common one you'll see, both a resistor and an inductor. Like a motor is a RL circuit because the motor has a magnetic field and wires with resistance. Your phase angle shift between the voltage and current, the difference, is somewhere between 0 and 90 degrees. It depends which one's bigger. If the resistive impedance is much bigger, you're going to have a phase shift difference closer to 0 degrees, like 10 or 20 degrees. If you have a very big inductor and a very small resistor, you're going to have a closer to 90 degree phase shift, like at 70 or 80 degrees. Either way, for this RL circuit, you're going to absorb real power P from the circuit. So this load is going to take real power P from the circuit. And this load will also absorb and take out reactive power Q from the circuit. So they're taking both of these out. If you have a resistive capacitive circuit, an RC circuit, this is a bit more rare in the power system, but we do have them. You'll have your phase shift, the phase difference between the voltage and the current is going to be negative 90 degrees to 0 degrees. Okay. Again, if it's more resistive, it's going to be closer to 0 degrees. So it'll be like negative 10 or negative 20 degrees. If it's if the capacitor is, if the impedance is mostly capacitive, so you have a big negative J impedance, your phase shift will be closer to 90 degrees. So it'll be like negative 70 degrees, negative 80 degrees. So this RC circuit will always absorb real power P from the circuit because you have a resistor, and it'll always supply reactive power Q back into the circuit. So just go ahead and remember, RC circuits will always put reactive power back into the system. RL circuit will always take reactive power out of the system. Okay, but no matter what, real power P is always getting taken out of the circuit as well, if there's a resistor present. Okay, that's the whole point of this chart, just to show you kind of like which devices affect real power P and which devices affect reactive power Q, because you're going to see RL and C's all over the place in circuit analysis, right? So we talked about P, talked about Q a lot. I mean, what does it actually mean in terms of everyday life? What is actually an example of real power P that we see every day? Anything that performs actual real work. Work is energy being spent to do something to make our lives better at the end of the day. You have light bulbs that light up. That's permanent energy, real power P. You have heat from a space heater or your actual HVAC unit if you have electric heater, right? That requires real power P because you have permanent energy dissipation, right? If you move things like a conveyor belt moving packages, a motor spinning and moving a pump, that also requires real work power P because you're physically doing work. You're helping the assembly plant, you're helping a product go be built. That's power being used from the utility. So that's what real power P means, actual work being done to the benefit of us as humans and society. How do we keep track of this real power usage? Because it costs money, right? If I'm a utility, I have to spend natural gas to power up my generator to give you energy for you to do work at your house or your plant. So I need to get paid. So we have a very typical SMUD power bill. If you look through everything, the thing that matters the most is right here, your rate. This is how many dollars you get per kilowatt hour. So on a non-summer off-peak load, so like basically at night. So right now it's not summer, so it's January, February technically. So off-peak means nighttime, right? Like anything past 8 or 9 o'clock is considered off-peak. Every kilowatt hour of energy you use in your house, you're going to pay 11.5 cents. Non-summer peak hours are for SMUD, I think is between 5 p.m. and 8 p.m. If you use energy there, you're going to be spending 16 cents per kilowatt hour. Okay. And they could keep track of how much energy used. So this particular person used 431 kilowatt hours off peak and 130 kilowatt hours on peak. Multiply these two numbers, they're paying $50 for their energy usage off peak and $20 for their on peak energy usage. Add them together, it's about $70 plus administrative fee and other BS fees, right? So a total of $100, and this is a 30-month interval. Okay, so remember what energy were we billed for? Fuel spent from the utility. Utility has to spend, we have infrastructure to keep up, we have energy we need fuel for the generators. All that comes in a package deal that you pay to the utility. Okay, it costs money. What's the unit of energy is kilowatt hours. Where do we get kilowatt hours? Remember, energy is always power multiplied by time. Power is the rate of energy used per hour. You multiply by number of time, how many hours you use. So if you're running something for 8 hours a day, you multiply power times 8. Okay. Our total is going to be kilowatt times an hour. So 1 kilowatt hour. Okay. And you can always take any device you have and look at the power ratings and see how much power you're using and how much it's going to cost. So let's say you have a gaming PC that has a 1,000-watt power supply. Well, that's 1 kilowatt. So if you're using it for Bitcoin mining and it's running full throttle for a whole hour, you've used 1 kilowatt hour worth of energy. So you have to pay 11.5 cents for that. If you have a 500-watt power supply and you're using it for 2 hours, that's 500 times 2 is still the same 1 kilowatt hour. So you're going to pay the same amount. Okay. So obviously, the bigger the power draw, the more expensive it's going to be. And the more time the longer it's on, the more energy it's going to use as well. Okay. What's an example of reactive power Q? That's a new thing we talked about today. Remember, reactive power is oscillating energy. It's that inductor spinning energy back and forth. No work is being done, but it still takes effort by the utility to power the magnetic field and depower it every cycle. So from a utility standpoint, we still have to put fuel in the generator. We still have to spend money to send current to you for reactive power, even though it's not doing any work. Now, first thing someone will say is that's stupid, it's wasting energy. Why would they ever use it? We don't want reactive power on purpose. We try to avoid it as much as possible. Unfortunately, it's part of the world. We can't get away from it. Any rotating machinery in your house, like this fan, this vacuum cleaner, anything that spins, HVAC, it's a motor, and motors have magnetic fields. Anytime you have magnetic field, it's a giant inductor. You're going to have to charge and discharge that magnetic fields. So inductors induce magnetic fields for motors and transformers to operate. This is your pole-mounted transformer outside your house. All three of these take reactive power. If I could make a motor that does not use magnetic fields, that does not use reactive power, I'm going to quit work today and I'm going to become a billionaire tomorrow, because that's breaking the laws of physics and we'll save billions of dollars. But realistically, that's not going to happen. So reactive power is here, whether you like it or not. We're going to have to deal with it. We could try to minimize it, but it's always going to be there. So from a circuit standpoint, whenever we do calculate power usage, we have to keep track of reactive power just as much as you're calculating real power P. That go hand in hand together, okay? So yeah, I kind of answered my own question, right? Your reactive power is useless and waste energy. Why do we have it? It's necessary evil when using motors, right? Here's a good question. Do we pay extra for reactive power? From a residential standpoint, no, we don't. So the billing for your house does not take into account reactive power Q. And the reason why is we don't run big motors. The biggest motors you have in your house are going to be either your HVAC system, your air conditioner, the compressor most likely, maybe the blower, most likely the compressor outside, or your dryer for your clothes. Those two are probably your biggest loads. But you don't use the dryer too often, right? I mean, like how many hours a week do you use it? Like maybe 3, depending on how many loads you do. The HVAC depends how hot it is. Could be something, but for the most part, it's not worth the utility. From a utility standpoint, I work for utility. It's not worth putting a second meter on the side of your house and keep track of a second power, right? Because realistically, a house does not use that much reactive power. Most of the house is real power P usage, and that's what you're billed for. Your meter outside your house calculates real power P. Okay. Now, for an industrial setting, that's totally different. Think of a giant oil refinery, Amazon warehouse. They have a lot of motors. The majority of their loads are going to be motors. That giant conveyor belt, that giant pump, right? The pressurizer. So there's 10,000 horsepower motors in industrial plants, very common. That 10,000 horsepower has a lot of reactive power built into it, a lot. Right? At this point, we're talking tens of thousands of dollars on a utility bill, millions of dollars per year. Yeah, we're going to keep track of that as utility 100%. Okay. So basically, residential area, you don't have to worry about reactive power. You don't have to pay for it. It doesn't show up in your smart bill. If you're going to be an electrical engineer in charge of of a oil refinery or a large manufacturing plant, you're going to get familiar with reactive power. You're going to look at the billing cycle. You're going to have reactive power billed to you. Okay. You're going to keep track of that. So it's just, I'm trying to show you realistically where does reactive power come into our lives, not just a mathematical concept in circuit analysis, right? So a funny factor is technically you could take a gigantic inductor and plug it into your wall socket and you won't get billed a single cent for using it, right? But utility you'll screw them out money for sure, but you technically won't get billed a single penny while the utility is spending an extra $100 a month to power and depower your inductor if you want to do that. So fun fact. Question is where you can get an inductor that big, right? That thing can cost like $5,000, and you're gonna need a pickup truck that's gonna weigh like 1,000 pounds, right? But it's a good thought process, exercise. So let's go ahead and summarize what we talked about. Two major components, real and reactive power today. So real power is permanent energy flow, P equals Vm Im divided by 2 cosine of theta V minus theta I. Reactive power is oscillating power in a system. Q is equal to Vm Im divided by 2 sine of theta V minus theta I. We want to power our loads to be mostly real power. Okay, that's what's doing real work. We want to minimize reactive power in our loads because that's wasted energy. That's the end of the day. So parents, from here on out, especially in the power industry, your managers are going to talk about real power P and reactive power Q. The instantaneous power, V of T equals all that cosine trick stuff, you're not going to see that anymore. Not too often. It's mainly these two are the driving power equations for all of power engineering, man. So I breathe, eat, and sleep this stuff at work all the time. We're talking about P and Q for power calculations. So just get used to seeing this. Okay. All right. That's all I have for today. We're going to come back next time and talk about some more stuff about power factor, blah, 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 blah. Okay. So we'll see you on a synchronous session later on this week. So I want to say thanks for showing up. You guys have a good rest of your day, and we'll catch you later. See you around.